So hello, everyone. Welcome to the Steel for Lunch. If we haven't already met, I'm AJ Darras. I work in the Steel Center, and we're happy to host today's presentation on winning or losing. It can be in the connections. Our presenters today are Brendan Cardiff and Dean Anderson. Brendan is from Collins Steel, and Dean is from Steadfast Engineering. I will hand over to them after just a few housekeeping items. So first, you will notice you were muted on entry. This is for everyone's listening pleasure and to reduce feedback and background noises. If you have any questions, please use the chat box, or you can raise your hand, and the feature is under the Participants tab. We will try to end on time at 1 p.m., but we may be going a bit longer to answer some questions. But if you have to leave early, we understand. Last, please visit thesteelcenter.ca to see other upcoming presentations. So let me introduce Brendan from Collins Steel. Brendan is the Detailing and Engineering Manager at Collins Steel. He has been in the structural steel industry for the past 13 years in a variety of roles, including connection design, engineering, estimating, and project management. Brendan has worked on some interesting projects in his career, including the CCIS North Lecture Theatres, the Royal Alberta Museum, and the Red Deer College Rec Center. He holds a Bachelor of Science degree in Civil Engineering and the Master of Engineering degree in Engineering Management from the University of Alberta. Dean Anderson is the founder of Steadfast Engineering. He has worked on structural steel connections on projects across Canada with a variety of fabricators for the past 14 years. Dean holds both a Master of Engineering degree in Structural Engineering and a Bachelor of Science in Civil Engineering degree from the University of Alberta. Awesome. So thank you very much. And thank you for joining us today. Thanks to Collins and Steadfast Engineering, both members of the Steel Center. And I'll now hand over to Dean.
All right, thank you. Gonna share my screen here. See if I can get this to work well. All right, so I'm up, I think. You can see that? Okay. So thank you very much for having us. Again, my name is Dean Anderson. I'm the founder of Steadfast Engineering, and we have Brendan here from Collins Steel. Yeah, we've worked together for, I don't know, a number of years, I guess practically that whole time, about 13 years together, so we know each other pretty well. We're going to discuss the fabrication of structural steel connections and how they affect the overall cost of a project. In industry, generally, I don't want to paint everybody with the same brush, but it's almost understood that if the overall weight of the building with respect to steel is low, then that's a good thing. It's going to be cheaper. That might be the case, and it often is the case, but there are times when the connections can play a really important role in the overall cost as well. The overall weight of the steel in a building might not be the only factor to consider. And we all want to be in a part of a project that's on time and on budget. And in the world of structural steel, the steel connections are a significant part of the overall success of a project. So that comes up with our title. That has nothing to do with the election, as Dr. Driver mentioned. Winning or losing, it can be in the connections. As we speak and as we carry on, feel free to put any questions in the chat. We can visit those at the end. I find it's good to put them in the chat sometimes, just because if you have a question as we're speaking and you don't want to forget, you can just throw it in the chat and we can look at that at the end. So the plan, this is what we're going to look at today. First of all, we're going to kind of scratch the surface on some of the different connection choices that we have. There's so many. It's kind of amazing to think, like I've been doing this for 14 years and I still run across new connections to design and new connections to kind of figure out. But hopefully we can give a bit of an idea of the variety that's out there in the world, so you can get an idea of how many different choices are out there. Then Brendan is going to get into the economic factors. He's the expert in the cost of these things, how much it costs to fabricate. And he's going to get in some insight on the factors that are involved in the fabrication cost of certain connections. And then we're going to look at some possible solutions. Some things to consider that you can implement today now to overall lower the cost of an overall project through the design of the connections. And we're going to look at a couple of things that still need some developments, things that can happen in the future also. So let's start at the beginning. Start at the beginning when an engineer wants to design something. Structural steel building, it could be a bridge, it could be a module for the oil field. We're going to look at this example here. This is a wireframe model of a building that actually Steadfast we were going to do and got a fair amount down the design process, and the whole thing got canceled, so it never actually came to fruition. But this is the way it starts. It starts with a wireframe model. So the building over here, you can see that it's just got lines kind of all over the place. And that's how the building starts in the design process. You lay out all of this geometry, where all your columns are going to go, all your beams, all your bracing. And then in the software that you have, you can put in the applied loads. So how hard the wind's going to blow, the snow on the top, the loads that are inside the building, if you have machinery or people or whatever it may be. And the software helps with the design of these members. You can kind of hit go, start, and let the thing run. And oftentimes the software can be set up and is set up so that it optimizes the weight of the structural steel in the building. So the software will spit out a whole bunch of columns and beams and braces that are the lightest possible. And that, again, might be the best way to do it, but it might not, depending on the connections in a building. At this point, the connection design isn't completed yet. The engineer is really just looking at the beams and the columns and the main members of the structure. Then a fabricator is hired. So the guy who's actually going to make this stuff, he's going to weld it together and put it up in the field. And this is where the connections really start to get discussed in more detail. Again, this is a bit of a generalization. There are times when the fabricators are involved earlier in the process, but in general, this is the way it happens. The structural engineer has designed the building. He's chosen all of his columns and his beams and his members. And then they hire out a fabricator. They say, okay, we want to hire Colin Steel to do this structure and fabricate it and build it for us. And that's when it starts getting looked at in more detail. They'll hire, depending on the fabricator, they might hire somebody like me at Steadfast. We specialize in structural steel connections. They hire us to design those connections for them. Colin Steel has their own engineers on staff, so they'll look at it themselves. But this is when it really starts to look, in a project, the connection design really starts to get looked at in more detail, starts to get figured out. And the reason for this is that there's so many different ways to connect steel together. You might have heard the phrase, there's more than one way to skin a cat. And I don't know, I find that phrase kind of horrific. So we'll change that. We'll say more than one way to peel an orange. I think that's a lot better. The cats will like that for us. But often the fabricator has different machinery, has different processes, has different ways to fabricate the connections. And so they want the connections to suit their process to lower their overall cost. So that's why the connections aren't designed at this point, or they're waited to design until this point, until the fabricator is hired so they can have that input on how the connection is designed. You might think it's kind of utilitarian, and it certainly is to an extent, but it is an art form really to design some of these connections. This is one sample that we did. We were working with Colin Steel on this one, and it's a connection that we designed for the Royal Alberta Museum. So it's a pretty complex node. We had moment in here. We had a lot of big forces. So there's a lot of different ways that you could have connected this together, and it took a lot of creativity and back and forth with fabricator, with the engineer of record, the person who designed the steel structure overall, on the best way to connect this and put it together. As a sample, this is the sketch, or at least part of the sketch that went in to describe this connection. So it's kind of interesting to see. So let's get into some simpler connections. Let's look at kind of what is involved in some different connections that are out there so we can see some of the variety and the choices that are out there. Beam to beam. So we have one beam and another beam that's going to connect into the other beam. So one beam is supporting the other beam. So again, you might think there's limited options, but there is a lot of different options. We're going to look at three. And what I want you to do as an audience, when you're looking at this, try to think of the number of parts that are involved in each connection and the amount of labor it might take to fabricate this connection, to create it. So the amount of labor that might be involved. This first example is what we call an end plate. So we have a plate that's welded to the end of the beam, hence the name end plate. And we have one plate and we have 6 bolts. There's 3 here and 3 on the other side of the beam that you can't see. And at the top here, this is what they call a cope. So this is where you cut the top of the beam out so it can fit under the top flange of the supporting beam. So this is one example. The copes at the top can be quite labor intensive, because if you don't have a certain machine that will do that for you, there's a guy out there with a torch who's got to mark all this out. He's got to take a torch out and he's got to cut every one of these copes. So if you have 1,000 of these beams, you can imagine that that's going to be a pretty significant impact on the project. Another option, we can do what they call a double angle connection. So it does the same job, except instead of having a plate, we have two angles. We have one angle on this near side and another angle on the opposite side that you can't see. We have a few more bolts. So we have 3, 6, and 9 bolts. The 3 on the opposite side you can't see. So there's more bolts, but the advantage to this one is that there's no welding. In this end plate, you would have to weld this end plate to the end. And in this one, you don't have to weld. You still have the cope at the top, so that's kind of a wash. But you don't have that welding. So that could be an advantage depending on the fabricator. A third option is what is called an extended shear tab. So here we have the same amount of parts as the end plate, except it's arranged a little bit differently. And it's welded to the web here, and it's supported by 6 bolts again. But the big advantage to this one is that you don't have to cope. This beam is cut square on the end. There's no extra cutting that has to be done, and it can be brought out past this supporting flange. So that's one of the big advantages here, is you don't have that cope. So which one is the cheapest? You know, you think about it, and it really depends. It depends on the fabricator, depends on the machinery that they have. These are some examples that Brendan's going to look at in quite a bit more detail as this beam-to-beam connection. And you can see the different, or the factors, the economic factors that will go into your choice of the way you want to do this. Some other examples. These are moment connections. So this is when you want to transfer a torque or a moment from a beam to a column. And in these few slides, we're going to introduce the idea of shop welding and field welding. So again, something to keep in mind with respect to the labor of a certain connection. If you were to connect the moment, this connection in real life, you would have to field weld this connection. You'd have to put this beam or this column up on site and lift this beam up into place. You'd have to get a welder, some guy, depending on how high it is, he'd have to get into a man lift of some kind. And you have to get up there and you have to weld all of these little welds on site in position, which is kind of difficult. So in general, if you want to do your welding, it's better to do your welding in a shop. If you're in a shop, you're in a much more controlled situation, a much more controlled conditions. You have your welding machinery sitting right near you. You can arrange your pieces on a bench in front of you so you can improve the position that you're welding. You don't have to get up in man lifts and kind of fly around in the air. And weather is actually a pretty big factor too. In welding, you have to have a certain amount of shielding when the welding takes place. There's a little bit of a gas, depending on the procedure you use or the welding method you use. You have to protect that application of the weld metal to the joint. When you're in a shop, you can control that a lot better than when you're in the field. If you're in the field, if it's a rainy day, a windy day, a snowy day, that will all affect your welding and how it works. So this first example is one way to connect a moment connection. So this is a fully field welded connection. The second way is a different way to do it. So instead of field welding, you can shop weld all these plates on, and then you add some bolts. So they can just lift this and put it into place. So again, where is your labor spent? In this connection here, your labor is not really going to be spent in the shop because they don't have to really do much work in the shop. They just cut the beam and cut the column and send it out to site and let him deal with the issue. And in this one, you would have to do this work in the shop, but then in the field, all you have to do is put this beam up, insert the bolts, and you're done. It's good to go. The third option here, this is very similar to this middle one, except we have a bunch of reinforcing in the column. This is one thing that can affect, or the choice of your column size can affect this connection. If you choose a column that's nice and strong and sturdy, when you apply this moment to the side of this column, the column can take it. You don't need to add in all of these plates. If the column's not quite strong enough, you would have to add in all these plates. So we have some horizontal stiffeners here. We have what they call a web doubler. So this is a plate that reinforces the web. The web might not be strong enough to take the forces in there. And again, this is a decent amount of work. And if you can talk to the engineer of record, if you can say, hey, can this column be made a little bit heavier so we can avoid all of this shop labor? So again, which is the cheapest? If you think about it, it really depends. Depends on your situation, depends on the fabricator, depends on the erector, depends on how they want to do things. So it really depends on which choice you want to choose for moment connection. To introduce a couple of brace connections, we're kind of keeping it simple here. We're just going to look at a couple of examples of kind of very simple brace connections. In the seismic world, brace connections can actually get quite complicated and quite large and a lot of work involved. But this will give you an idea of the choice between, again, field bolted or field welded and where you want your labor to go. So if you think of the number of pieces in this brace connection, we have 1 plate and 4 bolts. You have to take a torch and you have to slot this HSS brace, this hollow structural section, and insert that and weld it. In this one here, we have way less pieces. You still have to slot the brace, but you don't have to weld it until you get on site. So the erector will have to do this. So again, he'll have to get up in a man lift and he'll have to weld up here, and then he'll have to reach over his head, get underneath this, reach over his head and weld this weld that's underneath. So again, which one is the cheapest? Really depends. Depends on your position, where you are in the overall project. I think if you're the erector, this is going to be more expensive. And if you're just a shop guy who doesn't erect, this would probably be the least expensive for them, because then the field guy would do all the work. So I'll hand it over to Brendan, and he's going to talk about some of these economic factors to consider. We kind of scratched the surface on maybe some things to think about with respect to where the labor goes and where it's distributed between the shop and the field. And he can talk a little bit more in detail about some of these economic factors involved in the fabrication of structural steel connections. So I'll hand it over to Brendan.
Okay, thank you, Dean. So as Dean mentioned, there's many factors to consider when thinking of economical fabrication. So Dean's already talked about some of the ones that are listed in the first bullet. So I'm going to quickly talk about what's down in the second bullet. So where would you spend your effort? So the ratios that I have here are averages of the relative time it takes for them to complete their tasks. So like in general, for engineering to design a connection, it takes about 1/8 of the time that it takes to detail it. The time it takes to detail, it's about 1/4 of the time that the shop would take to fabricate that connection. And then, so this last point is a little bit different, but if you were to compare how long it would take the shop in the field to do the same thing, the shop is probably going to do it in about 1/3 of the time as the field. So generally speaking, you want to try and pull work from the field to the shop, and this can be done with either bolted connections or welded frames. And so it's also more common, because of the increased labor in the shop in the field, to spend more time in detailing and engineering to come up with efficient connections. And then obviously this would reduce time in the shop in the field. So we're going to talk quickly here about weight versus labor. So as an average, the cost of about 150 pounds of steel equals 1 shop hour. So we need to consider whether it's more cost effective to add material weight to save fabrication costs. So if the fabrication costs and the weight were a wash, I would still recommend to take the labor savings, because that just means that it'll flow faster through your production facility. So I'm going to do a little costing exercise of a beam to an HSS column connection that has to transfer axial load. So on the top left, we have a plate slotted through the column and then connecting to the 2 beams with bolts. The one in the middle is what we call a doubler plate connection. So essentially, in this case, we had to reinforce the walls of the HSS in order to effectively transfer that axial load. And then another option is for us to upsize the column so that the walls itself are strong enough to transfer that axial load. So which is more cost effective? So in this case, upsizing, well, let me start off by talking about some of the parameters. So I've assumed that there's about a 250 kilonewton axial load, and the column's about 3,700 millimeters, which is about 12 feet, which is going to be kind of a rough floor to floor height in a building. So the HSS costs about 73 cents a pound, and the plates about 53 cents a pound. So in this case, upsizing the column comes out to be the cheaper option. But as you can see, there's an upcharge in the material cost, but it more than offsets the savings in labor. So yeah, the labor is about $95 versus in the other options about $145 and $165. So in those other two options, the material is cheaper, but the labor is more expensive. And so the most expensive for us at Collins would be to have to weld on the doubler plates because there's just more parts to fit and more welding. So now I'm going to spend some time talking about the shop equipment that fabricators might have. So I'm going to give you a rough idea of the cost of each piece of equipment so that you can appreciate the cost of owning them, and then, you know, which might help you understand why fabricators don't have all of the equipment that's out there. So the first piece of equipment that we'll look at is a drill line. It costs about $750,000 or a little less, a little more, depending on which piece of equipment you're looking at. So in Colin's shop, the material will flow from the wall behind the machine towards us. And in the opening of the machine, it houses the drill head, and then there's these little rollers that measure the distance that the beam has traveled. So the benefits of this machine is that it uses CNC to automate the control of the drilling tool. So CNC stands for computer numerical control, and essentially this means that the machine follows a coded programmed instruction, which is created by our detailing software. And then this instruction is based on a coordinate system, and the machine operates without the need of without manual control from an operator. So the operator doesn't have to punch in any numbers, they just load the file, and because they know which piece is flowing through, and the machine does the rest. So in the picture on the bottom left, the machine drills the holes that are highlighted in red. And then this machine has a high-speed drill that can drill, you know, the holes in a matter of seconds. So the next piece of equipment is the plasma drill table, and these cost about around $850,000. So the drilling head is a high-speed drill similar to that on the drill line, and then it has a plasma head. So the basics of plasma cutting is that it involves sending an electrical channel of superheated gas from the plasma cutter through the piece of plate. So you can see there on the, I guess in the middle picture, it shows the, you know, the bright light. That's the plasma going through the plate, and all the sparks are what happens when it's doing the cutting. So in the picture on the bottom left, it first has to drill the holes highlighted in red, and then it cuts the perimeter of the plate with the plasma cutter. And so we cut, on this machine, we'll cut stiffeners, extended plate shear tabs, end plates, plates that we slot through braces. So it's a very useful piece of equipment. The next piece of equipment is a punch and shear, and they cost about $150,000. They automate the punching and shearing of angles and flat bars. So we use this for single or double bolted or welded angle connections. So in our shop, the material flows through the wall on the right through the machine. So the small parts will drop into the bin on the bottom left, and the larger pieces will roll out onto a table that's off to the left of the picture. So the benefits of this machine is that it uses CNC to automate the punching and shearing of the flat bars and angles. So in the picture above, it first has to punch the holes. So I don't know if you can see all the hydraulic cables on the right-hand side of the picture, but those are going to the different punches. And then at the very end of the machine, kind of right before that little bucket on the bottom left, there's the big shear. And then that cuts the pieces to length. So some equipment that other shops might have, they might have a coping machine. So as Dean discussed earlier, coping can tend to be, well, if you don't have a coping machine, it's a manual process. So that picture on the bottom left, you're having to cope the top of the beam so that it can fit under the flange of the other beam and connect into to the web of the main girder. And then shops might also have robotic welding, which, you know, on the right picture on the right, it can take the shear tab, fit it in place, and weld it. So a coping machine costs about around $1 million, and then robotic welding, you know, they're going to be north of $1 million. I've heard from years ago they were, you know, $3 million. So it's a very expensive piece of equipment. So I'm going to now take you through an example of beam-to-beam connections for Collins' shop. So we have a drill line, a drill plasma table, and a punch shear. So for the different connections that we've talked about, or that Dean talked about, end plates, double angles, or shear tabs, the shear tab seems to work really well for our shop because it best utilizes or maximizes the equipment that we have. So I'll now take you through an example of some framing on a project that we're currently working on, and then I'll show you how we would cost a shear tab versus some angle connections. So this is one bay of many where we have beams framing in, you know, making up the framing of the roof. So the shop drawing on the bottom left or on the bottom right are the ones that are highlighted in the picture. So these beams are very easy to fabricate as they only have holes that need to be drilled, and these can be done by our drill line, and then they can bypass fitting and welding stations. So approximately each beam would cost us about $50 to fabricate. That doesn't include the material, that's just for the labor. So then those simple beams have to connect into the beam that I have highlighted on the left-hand side. So in that bay, this is the only beam that has manual fitting. And then so by concentrating all the connections to this beam, it allows us to only have to handle one of the 4 beams in that bay. So the cost to fabricate that beam is about $450 in our shop. So here I haven't shown examples of the angle connections, but you can see what it would look like in the bottom left. So if for our shop, the shear tabs option would be about $600. And if we went to the bolted angle and had to do copes, the main girder would have a little bit less fabrication costs of about $240, but then all the beams that frame into that main girder have to be coped. So the labor for those would cause the cost of those to go to about $400. So for a total of $640. So the shear tabs result in a 7% savings in fabrication. Like these are just estimates, but I hope it gives an example of their respective costs. So the small savings doesn't seem to be significant, but it adds up when they happen hundreds of thousands of times on a project. So in summary of the economic factors, a fabricator's CNC equipment plays a large role in determining what is most cost effective for them. So as we have demonstrated, the connection choice can make a difference. Spend time up front in detailing and engineering, focusing on fabrication and field efficiencies. And so as a connection design engineer, if you consider these things, you're well on your way to having a successful project. Okay, Dean, back to you.
All right. So solutions. How can we make sure we implement kind of what we know about the fabrication of connections and how it's all put together? The first way really comes down to how a project is organized. The typical way of doing a project is as we described earlier, where the engineer, the structural engineer, is going to design the overall building, and he chooses the beams and the columns and all the different members involved. And they essentially become like a fixed thing. They can't be changed. He's done. He's done his job and he's moved it on. And the fabricator now designs the connections. And we saw one factor with the moment connections, where this reinforcement here could be a major cost. If you remember when Brendan was saying about that shop labor, if you could spend that time up front with the design engineer and do a project in the sense where it's a design build project, and you think about these connections earlier on in the process, you could choose a column that would be just a little bit heavier and it wouldn't have all that reinforcement. So, you know, that 150 pounds is one shop hour. If you think about that, this column might be a little bit heavier, but how much shop labor is that going to save? And you can save a significant amount of cost if you do this sort of thing. So if you have the fabricator and the connection design engineer involved early in a project, that's something that can really result in the overall cheapest and most cost-effective options for a steel structure. It's one of those things that can really, I guess the cost can really get large very, very fast when you start dealing with hundreds of these types of connections. There's some industrial projects I've worked on in the past where we're doing these types of moment connections, and there might be these things repeated down the line of a pipeline where you have several steel structures supporting one big long pipeline that goes on for a really long ways. And this connection is repeated like, you know, 1,000 times or 100 times, you know, multiple times, that can really affect the cost of the project. So if you can save that, you know, $100, $200 of shop time or more per connection, you can really save a lot of money in a project and really drive the cost of the overall project quite a bit down. So this is something that could be done right now. It does do it right now. There's certain project organizations right now, the way you can set up a project and when you get the different stakeholders involved early enough, that it really does this. It's something that can happen right now. It'd just be good if it happened more often, because you really could improve the overall cost of a project if you do things in a design build sort of a project setup. Another one, this is one of these things that you learn if you're a student listening and you haven't worked on, I guess, real construction projects yet. You'll learn when you get out into the real world. You might think engineering is just about math and design and figuring out the, you know, the stress and strain of materials and how all this stuff works and gets put together with all the numbers. But engineering is really a lot about communication skills, social skills, maybe good negotiation skills. When you have these skills and you have this clear communication between all the different parties in a project, you can really come up with good results. Sometimes you might assume that one guy in a project wants things done a certain way, so you kind of run down down the path of designing a whole bunch of connections, thinking they want it a certain way because you didn't ask, and all of a sudden you got to redo all your work. You know, so that adds cost to the project overall. So this idea of clear communication is really essential to come up with really good solutions, is have that open dialogue with all the different parties. And it can be with the engineer of record, the architect, the fabricator, the erector, the guy who puts it up in field. If you have these this clear communication, this is something that can really affect the project positively and drive that cost down and do things the best way possible. The Steel Center is actually working on it right now of trying to modernize the flow of communication between the different stakeholders in a project. So this is something I'm kind of excited about to see what comes out of that. Maybe there is some new technology or new process or idea that doesn't quite exist yet that can improve this this idea of clear communication. Again, you might think it's something that, well, of course, everybody's going to talk to each other, but in reality, it doesn't actually happen. It can be quite difficult to communicate with the people that you need to at times, just the way the projects are set up nowadays. Sometimes people are pretty protective of their knowledge, and they want to really monitor the flow of who talks to who and who discusses what amongst different people. So that idea of communication can really affect a project overall. With respect to me as a connection designer dealing with fabricators, this is another thing that if you kind of narrow it down to the design of a particular connection, again, I have to talk to the fabricator and I have to say, okay, do you have a beam line? What, you know, do you want to do end plates? Do you want to do double angles? Do you want to do shear tabs? Because again, I can assume that they want it a certain way. I could design the whole project and they go, oh, no, we don't want double angles. We want end plates, or we want extended shear tabs. So I got to redo everything. You know, so you can really affect the cost of a project that way. Sometimes I deal with detailers only and not the fabricator. So again, if that communication is blocked between all three of those parties, me and the detailer might think, oh, okay, they want to do it a certain way. And if it actually goes through and the fabricator has to fabricate all this stuff that doesn't suit their process, that can really drive the cost of an overall project up. So it's one of those things that really should be discussed and on the top of your mind when you're out there working in the real world on a project, is have that open line of communication. If you're ever in any doubt, make sure that you ask, talk to the people around you, and facilitate that collaboration process, because that can really help drive the overall cost of a project down. This is one Brendan really talked about, is spend the time up front. Again, this is another strategy that can be implemented when working on a project. In our fast-paced world, we can get caught in that trap of rushing through projects. The challenge of this is timeline. Typically, when I'm asking for a timeline from somebody who wants a design, the most typical response is ASAP in all caps with exclamation points, as fast as possible. You know, they have that pressure on them of getting the project done, and this can develop into a mentality of just get it done, we'll fix it later. And that happens really from the start of a project and can filter and trickle all the way down through a project with this hurry, 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 hurry. And so you don't do things properly up front, and it costs a lot of money down the line. And the earlier you deal with these potential issues, the cheaper the overall project is going to be. The longer you wait to come up with the best solution, like a connection design, the more expensive it can get. There's a lot of people along the line that have a really good input, the detailers, the people who draft these things. They have a lot of good experience. The erectors are some of the most valuable guys to talk to, because they're the ones who actually have to lift up the steel and put it in place. All the fabricators have such good information to share about the best way to do things. So again, spend that time up front to work these issues out earlier, and that's going to save money down the line. That time spent on drafting and engineering is cheaper than spending that time in the shop. The time that you might save in the shop is cheaper. The time that you can spend in the shop is cheaper than if it filtered down to the field. So you want to work these issues out as early as possible in a project, so you can save money overall. The next one is one that again is still in the works of figuring out the best way to do this. This is machine learning. Again, this is something the Steel Center is quite involved in, and is kind of on the cusp of developing something that's really exciting. And it's got a lot of potential in really saving money in a project. It's an idea of using computing power as kind of a brute force to develop an iterative solution with all the parameters involved to come up with the cheapest solution overall. And again, if you can do this early in the project, if you can have a software or something that can work out, some sort of machine that can work that connection design with maybe even some costing of materials, shop labor, erecting labor, that kind of thing, if they can have all that factored in to machine learning right at the beginning of a project. So instead of just spitting out a wireframe that's light, it can spit out a wireframe that maybe optimizes the connection design inside that whole process to come up with the best overall solution. Again, it's a big challenge to do this. The amount of parameters to input into this machine learning that it has to use to learn is kind of staggering. I try to think about it, and I think about how much you'd have to implement in there so it can think about this stuff. You'd have to implement maybe even live steel and labor prices. Maybe it can be tied in from an external source. So when that external source updates its material prices, its labor prices, it can be fed automatically into the machine learning. It can look for that stuff. Maybe the processes and equipment for each fabricator can be input into the machine as well. So it can choose the best option overall for a certain building and the certain stakeholders that are involved in a certain construction project. It's an area of research that's really growing, and it's going to grow into an excellent resource. It is really the way things are going. So it'll be exciting to see how this can impact the overall cost of a project when they include connection design in this machine learning. So brings us to the end. We've seen that the weight of a building may not be the most important factor in the overall cost. The connections are an important factor in the overall cost of a project. It's something that heavily impacts the overall cost and impacts a lot of people that are actually putting this thing together. So hopefully we've provided a bit of insight on how connections are fabricated. So when you get out there and you're part of a project, you can be part of a project that's on time and on budget, because you can think about how things are put together and the different ways that things are assembled. And think about that when you're working on your project, so you can implement some of these tools to have those projects that are on time and on budget. So I'll turn it over now to questions. I see we have some in the chat. It looks like there's a lot of discussion in the chat, actually. So we'll see what we have in there. And again, if anybody has any questions, feel free to unmute yourself and speak up. think there's a lot of discussion in the chat, so I'm not sure how much I want to start with all this. We got plumbing tolerances from Robert Driver, from Dr. Driver. I wonder if Brendan should answer that one. He says, what about plumbing tolerances for the various beam to column connections?
Yeah, it's not necessarily just about plumbing the column. My question is also related to how does the different type of connection, how, is there more adjustability if you try to bolt your connections versus weld them, that type of thing.
Okay.
Well, what we've found, Dr. Driver, is that like if you go with like a welded end plate connection bolted to say a wide flange column, there's a lot less, let's say, flexibility, because you don't get any, let's say, slop in the bolt holes to take up any tolerances. So anywhere where you've got bolt holes that are parallel, I guess, to the beam line, you have a little bit more flexibility, I would say. So even if you have a single angle connection or a shear tab, like they tend to work a little bit better. We've run into issues on buildings, definitely with end plates.
Yeah, that answers my question. I thought that might be a problem. So when you take the fabrication and erection into account, this might actually be a cost if it doesn't fit.
Mm-hmm. Yeah.
There's one issue that I've seen in several buildings with end plates is if you have a really long wall and you have end plates all the way down a wall, it tends to grow the wall. So you start putting up your beams, and as you go down the line, the last column is going to be out of plumb so far, because it almost seems to grow, like the beam line gets longer and longer. And that's due to like the little, like the paint and little imperfections that are on the end plates of the beam. So if you design the beam and you cut the beam so it's exactly the length that it's supposed to be, it's actually a tiny bit longer. So as that error propagates down the line of a building, it gets longer and longer. So that can create a pretty big cost to try to solve that. I've seen guys, the way they solve that is they cut and fabricate all their beams like 3 or 4 millimeters short, and then just provide a number of shims on site to try to shim up their column properly that way.
Yeah, and welding can also distort an end plate. So when you weld the webs, it can actually pull the, cause the plates to bow a little bit. Yeah.
Yeah, smiley face.
The question below about the A490 versus A325, we at Collins, we pretty much typically use a 3/4 inch A325 bolt. We find that it's easier because then the ironworkers on site don't have to have a bunch of different bolt sizes and a bunch of different kegs of bolts that they're carrying around and different bolt sizes in their pouches. So we tend to like to stick with a 3/4 inch A325 versus changing bolt sizes or grade. So for us, it's very rare to go to a bigger bolt unless we're working on a job that has connection forces that are much larger than we normally would see. So I don't know if you have anything to add to that, Dean.
Yeah, one thing that we've learned too from erectors is their feedback is that if you do have a 3/4 inch bolt, which is the most common bolt used out there, so a 3/4 inch A325, and it's not quite strong enough, instead of going up to A490 with another 3/4 inch bolt that the guy can mix up on the field, you'd bump it up to a 1 inch bolt. So either you go a 1 inch A325, and then I've even seen for projects that have a number of 3/4 inch bolts for kind of all the normal, typical smaller connections. And if you need something that has a really big connection, you use 1 inch A490 bolts. But you never have the same diameter of bolt on site with 2 different grades because they can mix them up. And there's I don't know, the chances, from what I've heard, the chances are decent. I don't know if it's likely, but there's a chance that the guy can reach in his pouch and grab the A325 and put it in the bolt hole that's supposed to be an A490. And it'd be difficult to determine that. But if you have 1 inch and 3/4, he can't fit a 1 inch bolt in 3/4 hole. And if you put a 3/4 bolt in a 1 inch hole, it's going to be really big and he's going to know something's wrong. So another thing that I've heard that they like to avoid is using 7/8 bolts, because you can go 3/4, 7/8 in 1 inch. And a 7/8 bolt will fit in a 1-inch hole, and you might not notice that it's too small. So the erector has a lot of input on kind of what's easy and quick and less confusing. You know, if you start doing things where he has to really look and really be really careful in the number of bolts of the way he does things, then it could cause errors, which could cause problems to fix. Because probably the most expensive thing is a field repair, something that was done wrong for whatever reason, it has to be fixed. If they're cutting stuff apart and, you know, taking beams down and refabricating stuff on site, that can be really expensive. You know, the costs go up huge if that ever happens. So we had another question from Jeffrey, where he says, please comment on double connections at columns and or beam webs over a column. So when two structural members on opposite sides of a column, web, or a beam web over a column are connected sharing common connection holes, OSHA mandates that ensures, one bolt has to be in place. So this is the safety connections. Share the same. Okay, as ironworkers erecting and installing the field, these designs are a matter of safety and should be considered a standard. So yeah, that's very true. I've heard them called safety connections or clipped connections. So the idea is that when two beams are connected on opposite sides and they're sharing the bolts through a web or a column or something, you have one of those cut out, so then you can put one bolt in and bolt it up and put the nut on, so that bolt or that beam has no chance of falling down. Otherwise, you have to kind of hold one of the beams up and put the other beam up too on the other side and try to get the bolt in there. And both of these beams are kind of sitting above, you know, potentially ironworkers' heads where it could hurt them. So yeah, I would agree that it should be a standard. It's something that we do often, if not all the time. The times where it's kind of a challenge sometimes is if you have a few number of bolts. We've even done end plates with just 2 bolts, so 2 bolts in a horizontal line. So that you can't really do a safety connection with those, but you know, if you have more than that, 4 bolts and above, then you can get away with the safety connection. So did that answer your question, Jeffrey?
Yes, thank you, Dean. Appreciate it.
Dr. Driver says one large HSS provider or producer claims that there's no premium for HSS columns versus wide flange columns. Oh, that's definitely a Brendan question. You agree?
Well, I think generally speaking, HSS is more expensive per pound than wide flange. However, it tends to be I think a fairly economical section in the sense that it's got the same section modulus in both directions, so you don't have to worry about the weak axis bending or buckling of the column. So I think in from a design perspective, it's an efficient section. So in commercial buildings, we generally see a lot of HSS used, and we've done analysis on collaborative jobs before where we usually end up going with HSS anyways. So essentially the costs end up kind of just being a wash, and we prefer to work with HSS over wide flange. So hopefully that answers your question.
Yeah, it does. I'm aware of the no weak axis thing and the cost per pound, but I guess then I thought, well, does the connections make it swing one way or the other? Because it might be, to avoid slot through connections and stuff like that. So it sounds to me like that maybe the HSS producer that I'm referring to is correct overall.
Yeah, I think on commercial buildings, we generally have, lower pass-through forces and things like that, like on larger buildings where you can't get an HSS to resist some of the forces, and then they have to go to a wide flange. And I mean, it's honestly, I think, pretty close, and it's probably just comes down to what's commonly used in practice. So I don't think it would be a big sway either way.
I think that's where machine learning might come into play. You know, when you start factoring in everything else in there, then maybe the HSS would be a better section, or maybe the wide flange would be a better section. Jeffrey had another comment about the 4 anchor rods at the base of a column. And yeah, that's a really good point too. This is something I don't really see the 2 anchor rods. I think Dr. Driver responded, S16 does allow for 2 anchor rods where special precautions are taken. So it is technically allowed to have 2 anchor rods in the base of a column. The reason for that is if you have if you have a base plate and you only have 2 anchor rods in it, when they put that column up in the air, there's not much keeping it from the column of flopping over, you know, and possibly potentially falling over and hurting somebody. So if you put 4 in there, that gives it a lot more stability to keep it from falling over. So I think those extra precautions or special precautions taken might be holding the column up until you get some beams framing in to stabilize the column. But it is something I don't see it very often anymore, is having those 2 anchor rods. So it's one of those things that it's good to see the engineers, the design engineers out there, that they are avoiding that for the most part. I do see it periodically, but it is fairly rare to do that. And usually when it is a 2 anchor rod column, it's usually in a very kind of small structure, not very tall or big. So hopefully the risk is reduced that way. So Ali Imanpour says, does the cutting effort or cost change when a beam end is cut to create an angled end with respect to the flange plane as compared to the beam cut to create a flat end? That's definitely a Brendan question.
So I think yes, the skewed connections are going to be more expensive, and it ends up one of the big factors is how, you know, wide the flanges are on the girder that those beams are tying into, and also the angle. But I would guess that they're, you know, skewed connections are probably going to be 50% more expensive than a square connection, probably regardless of which connection type you're using. Because now you're starting to add, you're not using fillet welds anymore. You're going to be welding with bevel groove welds, and in a lot of cases having to, you know, almost complete penetration weld those plates to the web. So so more often than not, it's actually probably the welding in these situations that add more cost. So I hope, does that answer your question, Ellie?
Yes, thank you. Do you have any idea about how much it can probably help to reduce the erection cost when you have such skewed connections in the beams? I can draw an example that that I have in mind in the screen. So let's say these are the columns and the beam stops on both ends, and your beam comes with this angled connections, and you don't need the crane to hold it while your erector is doing the bolts at both ends. So does this? I understand the fabrication cost. It may go up, but do you think that this will help reduce the erection cost in E4?
That's a good question. My gut instinct is saying no, because the extra fab cost is probably going to far outweigh the erection savings. Because generally what's going to happen in that situation is they're going to just pin those connections with 1 or 2 bolts, and then they're going to move the crane. So it doesn't end up tying the crane up that long.
Okay, thank you.
So yeah, you're gonna have a substantial amount of labor doing those skewed cuts. That's for sure. There was also a question above here from Sunil about is it more cost effective to use a heavier beam than calling up a camber? Again, I think it depends. Depends on how much heavier you have to make the beam. But if you're going to bump it up like 1 or 2 sizes in the beam tables, it probably would be more cost effective. But if you're having to, you know, if you're adding because it depends on the section and how thick everything is, but I mean, cambering costs on, you know, regular floor beams are going to be like $200-300. So if you add 300 to 500 pounds, it's probably going to be a wash.
Thanks for noticing that one. I missed that one.
Yeah, no problem.
As I scrolling down.
Does that answer your question, Sunil?
Yeah, it does.
You can always call and ask too if you want.
Yeah.
Okay.
Okay, so Joel Hamilton has a question about when does a bolt need to be nut tight versus slip critical? I guess the easiest answer is it's typically snug tight or nut tight, and you require slip critical in, I know a lot of the seismic code requires that, so you have to have the Class A surface in the slip critical connection. Another one is a lot of bridges. Anytime you have any cyclical action on a beam, so a connection is moving back and forth consistently. So a crane, a bridge, seismic is designed that way just so you can avoid the slip. That's when you would need that slip critical. I'm not sure if that's an exhaustive answer, but those are some of the most common places where you would need a slip critical connection. Does that answer it, Joel?
Yeah, it's a good answer. I've noticed that working outside of Alberta, you get a lot more slip critical than inside of Alberta, and a lot of different connections that I'm not used to when I'm doing projects, say in Ontario or BC.
Oh, okay. Eric has a question about, in terms of normal project delivery, what is provided on the drawings? Are you guys given the drawings and models or just the drawings? What's the current process that we use to take information and start designing connections in detail? Do we manually input information into Tekla or connection software? Are there processes that allow you to export structural models into connection modeling softwares? I think AJ would answer a bunch of these questions too about the importing and exporting stuff. As far as the information goes, probably the best answer is it varies. That's again back to that idea of communication and having a direct line to the engineer of record. Some drawings provide all the information and they're really awesome. They give you really good loading information of what's actually happening in the structure. Other ones will just give you kind of blanket statements on how to design the connections. You're often over designing the connections to meet those standards. I've used models and drawings. Recently did an industrial project where they provided a Tekla model, and that was how they gave the loads too. So you'd have to look at each member and see what loading information was on each end. And there was actually no structural drawings. We just asked questions back and forth and determined the connection forces from there. And then I communicated with the detailer to put the connections in. And I haven't yet manually inputted information into Tekla. Like the connection design information. I think Brendan has though, right? Has Colin's been getting into that a little bit?
Yeah, and we're even trying to automate it with programming between Excel and Tekla.
Mm-hmm.
So there's also questions about the models. So yeah, that varies. There's projects where both consultants, so the structural engineer and the architect, will provide the model. There's also projects where neither will provide a model or one or the other. So we're doing a fairly complicated school right now where the structural consultant provided us with their model, but the architectural consultants didn't want to share that information, or it's a policy of theirs to not share. Would be very helpful for us, but yeah, we were unable to obtain it on that job.
Did that answer your question, Eric?
Yeah, it did. Thank you very much.
You're welcome. Okay, so AJ's got a question about the different costs of machines. In the fabrication shop, does that reflect the cost of using each machine? For example, the machine costs this much per hour. Maybe we use it less. Is that taken into account when looking at the costs of projects to a fabricator? Or is it relevant for all cost savings? Again, I think that's a Brendan question. That's like a business analysis almost.
Yeah, I mean, it's definitely going to factor into the cost. And different fabricators are probably going to have different ways of dealing with that. So like It's a good question. It really depends, and it depends on how competitive the market is. Like, if you have the equipment and you have it paid for, then sometimes you can not charge for labor, or the cost of running that machine, and just take the benefit to help you win work. And then if times are a little bit better, you can charge more accurately, I guess. So it does depend, and I'm guessing different fabricators are going to have different ways of dealing with that.
Can I cut in here for a second?
Yeah.
Okay. So the way you always want your equipment running, and the best way to do that is run it 24/7. You'll get the most, because it's a fixed sum versus the variable factors that go into it. So of course, when you run it, you have to buy electricity, oxygen, fuel. You're paying that, but versus the cost of paying a human, you want the machine running all the time. That way you can take say if you ran that machine for 5 hours a day and it cost you $200, versus running it 20 hours a day, it costs you $50 an hour. So you can work it into that way. And what Brendan's saying as well is true. Like, you can delete your cost of fabrication, and it also depends on what machine you're running. A drill line uses a lot less variable than, say, a Python. A Python will burn it, and you're usually charged around $350 an hour, versus a drill line, which you can charge out as a man hour, because you're paying the operator and maybe a little bit more, like $25. Does that make sense?
Yeah, that's actually quite helpful. Yeah, thank you, Joel and Brendan. Yeah, I was just thinking, it popped in my head because I'm thinking about the different things we can incorporate into the big question of optimizing the process as part of the project that we're doing. So it's really interesting to hear that. Yeah, thank you so much.
Another thing to think of is, if you look at some of the really high-end automated steel manufacturers in the States or in Europe, they're usually running 3 shifts of 8. So they'll never shut down, and their welders keep going regardless, day, night, weekend. Because once you hit that steady flow, you can pay off your equipment a lot faster, or you're reducing your overhead cost, essentially.
Yeah, reducing like the downtime. Yeah, that's very interesting. Thanks.
All right, so we have a couple more questions. We're 103. Is that okay, AJ? Can we keep going?
Yeah, I think we could. Like, if anyone really has to leave, feel free. But we'll take the last couple of questions and then go to the steel squad.
Okay. So Ali mentioned or asked, do fabricators usually measure out of straightness or camber before the shapes are shipped to the site? And if yes, what is the tolerance? So the CISE Code of Practice refers to CSA G40 and ASTM A6 for tolerances. So they are measured for sure. Brendan, can you comment on that one? You'd be more familiar with that, I think.
Yeah, they are, generally measured. It's part of the QC process, and they vary. They're listed in S16. So I don't have them all memorized, but they're in the book. Yeah, I mean, usually I want to say it's like 6 millimeters every 6 meters or something like that you're allowed. It's somewhere in that ballpark.
Does that answer your question then, Ali?
Yes, thank you, Brendan. Thanks.
Okay, and Cameron.
You're welcome.
Asked, rocking, self-centering steel frames or bridges are gaining popularity among engineers. Is it possible to produce a curved shape, extended base plate for the column base using CNC machining instead of conventional flat base for such structures? I think he's referring to the kind of the cup, right? And the column sits in the cup. I think, and is able to rock with the seismic event.
Yeah, exactly. Yep.
Yeah, so the energy of the seismic event is dissipated in this thing rocking up, and it actually has to lift the building up. So that's where the energy goes to dissipate out in the system. I'm not aware of a CNC doing that. It'd probably be a machining process.
Yeah.
Yeah.
Yeah. Or like a cast plate that you'd have to buy.
Yeah, because I know the CNC machining, like, you know, machining system, you can program that in and it can machine out that rock shape.
So is it possible to make a curve shape base plate instead of a flat extended conventional one?
Could you repeat that again? What was that?
Oh, so I'm saying like, so in our conventional structure, we have extended base plate, it's flat. Like,
Okay.
make the extended portion as a curve shape in CNC machine?
I think what Dean said is you can, but it wouldn't be with like a plasma drill table, because with that machine we load set thicknesses of plate. So if you want to curve it, it would be a machining operation where they would have to use it'd be a machining tool essentially to be able to achieve that. And it would be quite expensive to get those machined. Does that make sense? Because our plasma table only cuts in 2 dimensions, and the way we change the other dimension is by changing the plate thickness that we load into the machine. It can't cut in that third profile or in that third axis.
Okay, thank you. Yep.
And I'm not sure if I understand the last question here. If you have a steel bridge column with 1200 millimeters outside dimension, how will you connect such a large diameter steel hollow column with the bottom flange of the cross frame, which will act as a pier cap in a steel bridge? So how feasible is that? Not sure if I'm picturing that, what reality would be.
So what I'm saying, like I have a superstructure is steel, and now I am placing my column, the conventional concrete column, as a steel column.
Okay.
How I'm going to like do the connection in the cross frame and with the steel column, because the steel column is very big. It's like 1.2 meter, but
Yeah.
my cross frame flange is not that big.
Oh. Yeah, that's a design question for sure. That'd almost be a brainstorm to figure out the best way to connect down. I have some ideas floating around in my head, but I'm not sure if it'd be easy to describe them. That'd be something, if you want to contact us after, like I can talk to you about that one after, and maybe we could have a closer discussion, because that would be interesting to try to figure out maybe the best way to do that.
Okay. Yeah, maybe I'll send an email, because we had a discussion with talking of rapid span. So he told that he hasn't seen those kind of things, but it might be possible. Yep. Yeah, I'll send an email to you.
Okay.
Thank you.
Yeah, just send me email some drawings and stuff, and I could probably take a look and give some better input. And so Brendan could as well, for sure.
Yep, thank you.
I'll put you guys in touch. Okay, sweet.
Yeah.
Awesome, lovely. Well, thank you so much, Dean and Brendan, from Collin Steel and Steadfast Engineering, our Steel Center members. I'd like to also take a moment to thank all 13 of our different industry members. See them on the screen, for making the Steel Center happen and supporting us in this. So thank you all very much for joining us today. I'd like to ask actually the presenters and the Steel Squad to stay on the call for our session afterwards.